The last video introduced the pentagonal numbers. This video introduces the amazing pentagonal number theorem due to Euler. So we've seen the integer partitions have this generating function. So if you expand this infinite product out as a series, you will get 1 plus 1x to the first plus 2x squared plus 3x to the third. There's a 3 here because there are 3 integer partitions into 3 parts. They are 3, 2, 1, and 1, 1, 1. So the coefficient of x to the n in this generating function is the number of integer partitions of n. Euler's pentagonal number theorem has to do with the reciprocal of this generating function. So if I divide 1 by this term, I will get the following. So I'm taking the reciprocal of the generating function for the integer partitions, and it turns out that if you expand this infinite product, you will get a series that looks like this: 1 minus x to the first minus x squared, plus x to the fifth plus x to the seventh, minus x to the 12th minus x to the 15th. So there are 2 observations I want to make about this amazing result. The first observation is that the coefficients of your generating function are always plus 1 or minus 1 or 0. 0 if the term's not there. For example, there's no x to the third term, so I guess technically that coefficient is 0. But the coefficients are either plus 1 or minus 1 in all terms. That's very unusual. And the second observation I'd like to make is that the numbers you see circled here, the exponents on x, are the pentagonal numbers. Well, at least half of them are anyway. So 1, 5, 12, 22, those are the pentagonal numbers. These other numbers, 2, 7, 15, 26, I'll say in a minute what they are, but they're related to the pentagonal numbers. So this following statement that I'm about to write down is known as the pentagonal number theorem. So let me make room for it by erasing what I just put here. So here is Euler's pentagonal number theorem. This product, I going from 1 to infinity, of 1 minus x to the I, is the sum over all integers k. So it's the sum over all integers, positive, negative, and 0, where I have negative 1 to the k times the pentagonal number x to the k, 3k minus 1, over 2. Now in our previous video, when we introduced pentagonal numbers, we saw that this was the formula for the kth pentagonal number. So that's my 1, 5, 12, and 22. But I'm summing over all integers k, both positive and negative. So when I plug in the negative values for k, I'm getting the other exponents, 2, 7, 15. So for example, if I plug in negative 2 for k, I will get negative 2 times 3 times negative 2 minus 1 all over 2. What is this? This would be negative 7. Oh, excuse me, plus 7. Plus 7. So I get this exponent here. So the positive values of k give me the pentagonal numbers, and then when I plug in negative values for k, I get these other terms. Okay, so that is Euler's amazing pentagonal number theorem, and I'm going to show you a wonderful proof of this fact by Franklin. So here is the proof of Euler's pentagonal number theorem. So I'm going to recall from earlier work on generating functions that the generating function of 1 plus xi, this is the generating function for integer partitions with distinct parts. Therefore, if I put a minus 1 in front of the x to the I, every time I take a part of size I get an extra factor of -1. So remember why this is the generating function for the integer partitions with distinct parts. It's because when I expand as a product, I can either take a 1 or an x to the I term. If I take a 1, that means don't take integer I in my integer partition. If I take x to the I term, it means select integer I to place in your integer partition. So if I put a -1 here, every time I get a new part in my integer partition, I have a negative sign. So thus, using the logic that we've seen in dealing with generating functions, this infinite product, I going from 1 to infinity, of 1 minus x to the I, this is the generating function over all n, where I'm counting all integer partitions lambda of n with distinct parts, where I have -1 to the number of parts in lambda times x to the n. I will define a sign reversing involution that pairs integer partitions of n that have distinct parts. So I will describe what's known as sign reversing involution I'll describe what that means in a second. A sign reversing involution, let's call it phi, that goes from integer partitions lambda, so the set of all integer partitions with distinct parts, so all partitions lambda with distinct parts, back to the set of all integer partitions lambda of n with distinct parts, such that the length of lambda will be the length of the output after I apply lambda through this function, plus or minus 1. This is called a sign reversing involution because if I apply the function phi to an integer partition, it changes the sign, the either plus or minus sign that's associated with the partition based on the number of parts that I see. Involution refers to the fact that this function phi will also be its own inverse. It's going to be a bijection that is equal to its own inverse. And what this is going to do is pair up all the integer partitions that correspond to a plus sign with all the integer partitions that correspond with a negative sign and cancel out opposite signed terms. Let me describe this function, and I think from there we'll see really what's happening. So I'm going to let t lambda be the number of cells in the top row of lambda, and I'm thinking of the Young diagram of lambda. So if you draw the boxes, you look at how many cells are in the top row, and you get t of lambda. And I'm going to let s lambda be the length or the number of cells in the rightmost staircase. That's an ill-defined term right now, so let me draw you a picture. So here's a picture. I'm going to have an integer partition, so I'll draw a bunch of left and bottom justified boxes. That'll be my French Young diagram. So here is my diagram. Okay, so here's my integer partition. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and 3. So I have the integer partition 8, 7, 3. It has distinct parts. I don't have a repeated part. T of lambda, so this will be my lambda, t of lambda will be 3. So t of lambda is 3. And s of lambda, that's the number of cells in the rightmost staircase. And what I mean by that is that it's the number of cells in this diagonal strip here. Here, let me draw this in red, actually. So it's a number of cells that are consecutive going up this diagonal here. So I have 2 elements in the stairs. The sign of this object is -1 because I have 3 rows, 3 parts in my integer partition. So the total sign of this object is a negative object. So this is a negative object. I'll put a negative here to remind me that -1 corresponds to this object. All right, so I have the number of cells in the top row. I have the number of cells in this rightmost staircase. The function phi, that's going to be my sine reversing involution, is the function which takes the stairs in this picture, removes them from this right side of the image, and places them on the top of the picture above this top row. So this is my function phi. I'll describe it in a second. But what it's going to do is it's going to take these cells in the stairs, and put them on top. So I'm going to get the new integer partition. It's going to be 2, then 3, and then 1, 2, 3, 4, 5, 6, because I'm going to remove the stairs. I'm only going to have 6 cells here, so 6, and then I think I'm going to get 7 cells underneath that. So I'm going to get 2, 3, 6, and 7. So to graphically depict what just happened, I think I put the red cells here. This will be phi of lambda. Now notice that now I have 4 rows, 1, 2, 3, 4, and I have a minus sign to the 4th power. In other words, this is a +1 object. This is a positive object. So I've paired a negative object with a positive object. Here is the general rule on how to define this sigma, or this phi. So here is the rule. If the top thing here, if the top of my integer partition is bigger than the number of stairs, like in this situation, move the stairs to the top. Okay, if not, so if the top of these cells here is less than or equal to the side of the stairs, so S lambda, undo the operation, do the reverse. And what I mean by do the reverse is you take the cells on top, remove them, and pad the side of the stairs with the cells. So in other words, if I started with this object, I would just go back to my original picture, because in this case, the stairs length is 2 in this picture. The top row has 2 elements. I'm in this second case, and so I would go back and see my original picture. So this is a sine reversing involution. It changes the sign. It's an involution. An involution is a bijection that happens to equal its own inverse. So that's what I have here. This pairs up all the positive terms in this sum with negative terms. And I've paired up almost everything. The only times that I can't do this operation are the times when I'll get positive or negative terms that are left over in this generating function. So I want to list, to finish the proof, when this operation fails. So this fails exactly twice. So this fails in two situations. I'm going to draw you the pictures of when this fails, and I think you'll see exactly why it'll fail. So here's case 1 of failure. Let's say I have a square. Let's say my square is side length 4 in this picture. And then right next to the square, I have a triangle of height 1 smaller than the square. So if I have a square here, right next to a triangle of cells, then this involution will not work. Why? In this case, the top is, in the picture, 4 cells long. And the stairs are also 4 cells long. So the stairs here are length 4, the top is length 4. If you try to perform one of these operations, neither one will work. Because if you try to remove the top and pad the staircase, then the top is too long. And if you try to remove the staircase and pad the top, then it's going to be sticking out too far. Because if you remove the staircase, then the top will only have 3 cells, and you're going to try to stick a row of 4 cells on top. That's not going to work. So that's going to fail. And the other case where you have fail is when you have a rectangle of a rectangle where the width is 1 cell longer than the height. So it's just like my square picture, except I added 1 more column, and then you have this staircase thing. That also fails for the similar reasons. The stairs now has length 4, and the top has 5. If you try to remove the stairs and put it on top, you'll get a valid integer partition, but you'll have 2 rows that have length the same. And we're not permitted because we're only discussing integer partitions with distinct parts. And therefore, you can't have 2 rows that are the same length in the picture. So these are the 2 cases that fail, and the only 2 cases that fail. So you can count in this case, if this square has side length k, then you can say that this case fails when I have k squared plus k choose 2 cells. In that case, I get, if you simplify the fractions, if you add them, if you add k squared and this term, you actually get the pentagonal number. You get the pentagonal number. This is k times 3k minus 1 over 2. And in this case, you will get k times k plus 1. That's the square with an extra column on it. So this is k. This would be k plus 1. And then the stairs would have k plus 2 terms. And if you rewrite this and simplify a little bit, you will see negative k times 3 times negative k minus 1 over 2. This is the pretend pentagonal number when you stick in a negative for k. So I get leftovers that aren't paired up only in these 2 situations, and they occur exactly when I have pentagonal numbers and these like pretend pentagonal numbers. Everything else will cancel. Everything else will cancel. And so that actually completes my description of Franklin's proof of Euler's pentagonal number theorem. This is proof due to an American mathematician named Franklin in the late 1800s, and this was proof that put American mathematics on the map. So before this, people mocked American mathematicians, thought they couldn't come up with anything great, and when Franklin showed this, that myth was dispelled. Okay, wonderful.